Master, good afternoon. I was waiting for other guys, but I think they're not yet here. The time is passing. Last time we had introduced Newton's laws, and we had introduced Newton's laws, right?
Yes.
So we can go ahead and introduce momentum. Then I wanted these people to be around. I don't want to introduce something new when they are missing. Can you try to check them out on a group?
No. Yes.
And see if we can get them.
We can't present at the same time.
Otherwise, from Newton's second law, this Newton's second law states that. What did we say Newton's second law was stating? Master, do you recall what Newton's second law states?
The rate of change of momentum is directly proportional to the applied force and it takes place in the direction of the force.
Thank you. The rate of change of momentum is directly proportional to the applied force and takes place in the direction of the force. So we had seen that force is actually equal to mv minus mu over t. And with this, you can see that force times time, if you cross multiply, will give you the change in momentum. Now, this is what they call impulse. This is what you're calling what? Impulse. So sometimes impulse, we call it the rate of change of momentum. Not the rate of change, we'll call it the change in momentum. So by definition, we can say impulse is change in momentum of a body. And say impulse is the change in momentum of the body. Or sometimes we can say impulse is the product or impulse is the product of a force, product of force and one can say impulse is the product of force and time. or the product of the force acting on a body and the time that force takes to act on that body. That can also be taken as impulse. Okay. So with that, we can end up using this impulse and borrow it to go for what we call momentum. Momentum. Whereby, if you recall, how do we define momentum from O level?
Momentum is a product of force and the distance moved in the direction of the force.
The product and what?
No, momentum is a product of force of mass of a body and its velocity.
Product of a body's mass and its velocity. In a straight line. The reason why we say in a straight line, because it's a vector, whereby the direction can change. It can be moving in a momentum can be acting in a given straight line, or momentum can change direction depending on the direction of the velocity, right? So it is from here that we can talk about the principle. The principle of conservation of momentum. Do you recall that principle? You recall that principle? Try to recall that principle and state it. Mercy. Oh, Mercy, someone has joined. Amina, you're welcome. Yes, Amina, can you state for us the principle of conservation of momentum? Okay. Amina's gone. Mercy has gone. Amina, state the principle of conservation of momentum. Amina? Amina, please state the principle of conservation of momentum. Amina, don't you remember? Okay, if you don't recall, we even have Esther. Esther, please, Esther, can you give me the principle of conservation of momentum? By the way, before we go to the principle, the SI unit of momentum, because we have said momentum is mass times velocity, then this is kgs in SI units times meters per second. So the SI unit for momentum is kilogram meters per second. Therefore, if we know that SI unit for momentum is kg meters per second, then I wanted to state the principle of conservation of momentum. Principle of conservation of momentum. None of you can recall the definition of this principle. At least I expected some people to be in position to remember what the principle states. Because we have all experienced this principle, or we experience it on a daily, whereby you collide with something, you meet something, you get in touch with something. Even when you're colliding with your bed, you're experiencing momentum. Even when you are clapping your hands, that is momentum. Even when your teeth are colliding, that is momentum. Okay? So with that, you discover that momentum is actually dealing with at least two items meeting or colliding. Okay? Now, if you get to know that you have at least two items meeting or colliding, then what does the principle state? The principle states that if you have two bodies that are colliding in a given direction, then the momentum those bodies experience before they collide is supposed to be equal to the total momentum they will have after the collision has occurred, provided you do not have any external interference or any external force that is coming in. So ideally, one can say, in a system of colliding bodies, states that in a system of colliding bodies, total momentum before collision is equal to total momentum after collision, provided no external force acts on the system. But someone can have it summarized in this form by saying, in a closed system of colliding bodies, total momentum is a constant. Total momentum is a constant. When we say it's a constant, ideally we imply that it's a constant before and after. It does not change the total of the momentum. So in a system which is closed, it also means that is a system which does not get interfered with external forces. That is what we call an external system. So in a closed, or what we call a closed system. So if you're in your bedroom and you've closed yourself in there and no one is interfering with your presence in the room, then you are in a closed system ideally. If interference, we are assuming it's humans, pets. Yeah. If you've locked yourself in a bedroom, then you are having no external interference. So you are in a closed system. So even here, when someone says in a closed system, total momentum is a constant. A system of what? Colliding bodies. Total momentum is a constant, meaning that the total momentum before is equal to the total momentum after. And the colliding bodies I talked about, if you items like clapping your hands, my hands are colliding. The momentum they have before collision and the momentum they have after they have collided, they might collide and move in the same direction. They might collide and split. They might collide and divert at an angle. So anything is possible. That is why we have to mention in a straight line or in a given direction. Is a constant in a given direction. When you say given direction, it means you're specifying the direction, whether it's still maintaining the same straight line, or it has diverted, or it has become static, whatever the situation will be. Now, they can ask you to use Newton's law. Which law? This one, which we call the third law. Yeah, second law. Normally, people will call it the second law. When you use Newton's second law, then you can be in position to go ahead and prove the principle of conservation of momentum. So you can say, using Newton's second law, using Newton's law, to prove the principle of conservation of linear momentum. Now, if you let the masses of the colliding bodies be M1 and M2, be masses of the bodies, then you let U1 and U2 be their initial velocity. Their initial velocities. You can let V1 and V2 be their final velocities. Then the time can be the time taken in contact. Then F1 can be the force on impact on M2. Then F2 be the force on impact on M1. Then from Newton's third law, which says action and reaction are equal but opposite. One force F1 acts on mass M2, then M2 is going to act back with another force which is in opposite direction. So it's going to be F1 is equal to a negative F2. That is why the force is negative. Then, if you did draw an illustration for this, momentum before they collided, when they collide, when they are colliding, we have F1 acting on M2. If this is our M1, M1 is going to experience a force F2, which is as a result of mass M1. This is M1, this is M2, this is U1, this is U2. Then after they split, when they split, M2 moves with a velocity V2, while M1 moves with a velocity V1. So at that instant, at impact, we have force F1, which is going to be equal to mass M1 times the change in momentum divided by time. This is V1, U1. Then for F2, we shall have mass M2 into V2 minus U2 over T. But we have seen that at impact, there is action and reaction. One force acts on another body, and the other body also reacts back with another equal magnitude force. Therefore, M1 into V1 minus U1 over time is going to be equal to M2 into V2 minus U2 over time. But this second one is acting in a different direction, so it's a negative. So if it's a negativity, the time is the same because it's the time of collision, the time of impact, the time they spend together when they're in touch. I told you when you clap your hands, it's a collision. The time your hands are acting upon each other, they are in contact. This left hand is pushing the right hand. The right hand is also pushing back the left hand. That is why they are able to remain stationary. For example, if I'm pushing them like this together, they are remaining there at the same time. But now, if I'm clapping and I'm releasing them, after colliding, you see that you don't put in any energy, you don't give them any push, but they just bounce off each other. So they collide and bounce, collide and bounce. As they collide, at that point where they are colliding, that is why they produce sound. Because some of the energy you have used to bring these hands together is lost in the form of collision with the fingers. And you know those fingers, partly they have some grips which make them rough. So with that sense, the fingers can also produce sound by losing some of the energy. So with that knowledge of losing some of the energy and then the collision, we have seen that one hand is acting on the other. So one hand acts on the other with equal magnitude of force, and the other also reacts back with the same magnitude of force, but in the opposite direction. So that opposite direction calls for a negativity. That's why we have the negative. But because the time of impact is the same, then that time can be lost by division. When you divide off the time, we shall realize M1 V1 minus M1 U1 is equal to a negative, open brackets, M2 V2 minus M1 V1. Sorry, M2 U2 minus V1, M1 V1. So, apart from Amina, the rest of you are mathematicians and your algebra, I trust, is pretty compatible now. This is area we are going to have a lot of algebra required. So Amina, I will need your patience and I will require you to ask me anywhere you see that I've left you in terms of my simplifications mathematically. But the rest of the guys, I trust that you can handle, or you can follow very easily. So I'm only worried about Amina, but in case she has any challenge, please Amina, raise it up and I see how best I can help you. So this is going to become M1.
Teacher, is that M1 V1 or M2 V2 on the second part where there's a negative?
M1 U2.
On the next line,
V2.
the one immediately above where you're writing, yes, there.
Oh, this is M2
U2.
V2 minus U2. Yes, this is correct and this is correct. Because it is the final velocity minus the initial velocity.
Line.
This one.
Yes.
It is, oh, this is supposed to be M2.
Mention any.
Oh, let me change it totally. This was supposed to be M2 V2 minus M1. I mean M2 U2. The momentum after for mass 2 minus the momentum before for the same mass. So we can have M1 momentum before, after for the first mass, minus M1 U1 is equal to M2, a negative, V2. When the negative penetrates the bracket, we shall have a positivity of M2 of U2. Now you can move this V2, M2 on the other side, where we shall have M1 V1 plus M2 V2 is equal to M1 U1 plus M2 U2. I have also moved this one this way to become a positivity, and I've moved that one on the other side. So in totality, M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. And indeed, this is our principle of conservation of momentum. When you look at the left-hand side, you only have total momentum before for both of them. When you look at the right-hand side, you have total momentum after collision, which is the momentum using velocities. Then the other one is the momentum, velocities after. Then this one is the momentum using what? Using initial velocities. Then this one is momentum using final velocities. Unless if someone has a question. you have any questions on that derivation?
Yeah, can you put back on the first page?
Okay.
I'm done.
Okay. I'll also send more notes for the write-up. Now, having seen what the momenta talks about, we have types of collisions. Let's talk about types of collisions. Esther, give me one type of collision you know.
Elastic collision.
Elastic collision. Where is our man? Is our man present? Cynthia, give me one type of collision.
Inelastic collision.
Inelastic collision. Thank you. Amina, do you recall something about the elastic collision? Some people say it takes place among elastic bodies. It is impossible. What are the elastic bodies? It can take place anywhere. Hmm? Elastic collision, we have one. Bodies do what? Bodies separate. After collision, have different what? Velocities. Then out of these two, both momentum and kinetic energy are conserved. So those are the basic items you need to know about elastic collision. So it's a type of collision whereby the two colliding bodies, one separate after collision and move with different velocities. And in that situation, both momentum and kinetic energy are conserved. Then for inelastic type of collision, the bodies stick together. Bodies stick what? Together. The bodies stick together. They move with a common velocity. They have a common what? They have a common velocity. And when you have a common velocity, it's only momentum that is conserved. And the kinetic energy is not conserved. So both momentum in this case, in this case, momentum and kinetic energy are not conserved, both of them, but rather we have only momentum conserved and Ke is not conserved. So we need to have that in mind. So having seen that, those become some of the characteristics of elastic collision. We have seen both elastic collision, both kinetic energy and momentum are, kinetic energy and momentum are conserved. In elastic collision, little sound is produced during collision. In elastic collision, the bodies remain undeformed because they have split. Then they also separate after collision. If you've seen vehicles collide on walls, yeah, on pavements, and they get stuck there, the sound they produce is not the same sound they produce when they knock down a border rider. A border rider will separate with a car, whereas this car will get stuck maybe in the wall, in the types of in the inelastic method or collision type. So the type where they separate, they do not produce a lot of sound, whereas the type where they stick together, they produce a lot of sound. Yeah. So in inelastic collision, let me first look at in the elastic collision. We have said both momentum, which is M1, U1 plus M2, U2 are conserved. This is what they mean by saying momentum is conserved. The momentum before is equal to the momentum after. Then also they have said kinetic energy is also conserved. So the kinetic energy before plus kinetic energy of the second body before is equal to their total kinetic energy after. This is what we mean when we say kinetic energy is conserved and kind of momentum is also conserved. Then in inelastic, it is only momentum which is conserved, which is M1 U1 plus M2 U2. When they get stuck together, you get M1 plus M2, and then they move with a common velocity V. So this is the definition for momentum after and momentum before for inelastic collision, whereas this one is for elastic collision, momentum and kinetic energy being conserved. So it is from here that we can be asked to derive the change in energy or the loss in energy under inelastic collision, because we see kinetic energy is not conserved, but in elastic it has been conserved, but here it's not conserved, so we have loss in what? Loss in energy. So we can be asked to find loss in energy under inelastic collision. So if we are to lose energy, this is what is going to happen. Firstly, we have seen that momentum before of the two bodies.
Excuse me, teacher.
Yes, please.
Excuse me, teacher.
Please go ahead.
Could you please go back to the previous page?
Okay.
Can you hear me?
There you are.
Yeah. Thank you, teacher. I'm done.
Now, if I was to get kinetic energy before, kinetic energy before, I would have R F M1 U1 squared plus R F M2 U2 squared. Then kinetic energy after. The kinetic energy after would be R F of M1 plus M2 times V squared. Now the loss in energy is the difference between the kinetic energy before and the kinetic energy what? After. With this difference, we shall realize our F. M1 U1 squared plus our F M2 U2 squared minus our F of M1 plus M2 times V squared. Then we can simplify. Can have half M1 U1 squared plus half M2 U2 squared minus half of M1 plus M2, but with a V squared. I can make V the subject from equation 1 by saying from 1, you can realize that V is actually equal to M1 U1 plus M2 U2 all divided by M1 plus M2. With that, eyes open widely here. Change in KE, that symbol which is like a triangle represents change. Change in kinetic energy is going to be equal to half of M1 U1 squared plus half of M2 U2 squared minus half of M1 plus M2 close brackets times V squared. We have realized our V is actually M1 U1 plus M2 U2 all divided by M1 plus M2 close biggest bracket, raise this to the square. This is where I need skills of algebra. Amina, please stay with us. In case I leave you somewhere, please raise the hand or press unmute, dial the unmute button, and then raise your concern. The rest of you who are mathematicians, I expect you to follow suit as well. So with this, I can factorize out the half because it's common in everything. Introduce biggest bracket, I'll get M1 U1 squared plus M2 U2 squared minus small bracket M1 plus M2 close small bracket, open biggest bracket in the second term, which is going to be the expansion of M1 U1 squared plus twice M1 M2 U1 U2 plus the expansion of the square of M2 U2 both squared, close that big bracket which is squared, all divided by M1 plus M2. Now the whole of this also is raised to a square, close curved brackets. Can people look at it before I can proceed? And I hear some questions because I expect questions here. But to remind you a little, this comes from A plus B expanded, you get A squared plus 2AB plus B squared. So our A is M1 U1, our B is M2 U2. When you raise it to the power 2, you expand, and the middle term is twice what you have before of the two terms. So that's how it came about. Amina, are you there?
Yes, teacher.
Are you okay?
Yes.
Okay, I think the rest you're fine. Any other person with a concern before I do more algebra? This area requires a lot of algebra. So I can divide.
Can you
Pardon on?
teacher, can you pardon on loss in kinetic energy from there, that little
Okay.
one.
We are looking for loss in energy. Yeah? If you have eaten food in the morning and you feel you're very energetic, and then the afternoon, maybe you are already tired, yeah? And you feel like you want to sleep, you feel like you can't do anything, it means you are short of energy. But in the morning, you are very vibrant, you had a lot of energy. So if the afternoon you cannot handle yourself, it means you have lost some energy along the way. Now the difference in the energy is, yeah, the energy you had before minus the energy you are having then. That difference between the two energies corresponds to the energy you have lost. So the energy you have lost is equal to the kinetic energy before minus the kinetic energy after. Whenever you have a loss in energy, the energy before was greater than the energy you have now. If it was an energy gain, then the energy you have now would have been greater than the energy you had before. So right now, the energy you have is less than the energy you had before. And with that note, the kinetic energy before can be subtracted by removing off the energy we have now. The change in energy corresponds to the loss in kinetic energy. So the kinetic energy we had before was that one. The kinetic energy we had after was that one. So you subtract the two, and that is where we are. Okay. So I think we are good. Are people happy with that?
Yes, teacher.
Okay, more action. Now check out this division. I have M1 plus M2 in the small bracket. I can divide the whole of that small bracket with this other small bracket, and I'll remain with power 1 in the denominator. Are we good with that division? If we are good with that division, I'm going to cross multiply. Because all these ones are whole numbers, I can assume they have over 1. So when I assume they are whole numbers, then this is what is going to happen. I'll have I open biggest brackets, M1 plus M2, close small bracket, open those two items, M1 U1 squared plus M2 U2 squared, close that bracket, minus, open biggest bracket, M1 squared U1 squared, a plus 2M1 M2 U1 U2 a plus M2 squared of U2 squared, close biggest bracket, close curved brackets. Are we still fine? We need patience here. There's a lot of algebra here. It's not complicated, but the consistency and stability we require here is for someone to be in position to be able to go slow, go through these expansions, and prove whatever the question wants you to prove. It's funny we don't have this item in mathematics. Okay, momentum is there, but me, I don't teach it in mechanics. I expect learners to teach themselves because they have covered it in O level. But in physics, we go into these details of momentum. So can we open this bracket, these two small brackets? Eyes open. There's also a challenge there. When you open these two small brackets, open biggest curved brackets, M1 times M1, we realize M1 squared, U1 squared. M1 times M2, we shall realize M1, M2, U2 squared, a plus. That is M1 multiplying. Can we now use M2 as well? M2 goes into the other small bracket confirming M1, M2, U1 to the square, a plus. M2 to the square, U2 to the square, minus, open biggest bracket, M1 squared, U1 squared, minus twice, M1, M2, U1, U2, a minus, M2 squared, U2 squared, closed curved brackets, all now is over. Oh, I had forgotten to write down there when I cross multiplied here. How come no one saw that? I asked you whether there is a challenge, no one answered. This was over M1 plus M2. Now, likewise, the whole of this one is going to be all divided by M1 plus M2. So divided by M1 a plus M2. More algebra is required by subtraction. We are going to lose M1, M2 squared. If you see M1 squared, U1 squared, vamoosh by subtraction. You see M2 squared, U2 squared, you see minus M2 squared, U2 squared, vamoosh by subtraction. Having vamooshed M1 squared, U1 squared, M2 squared, U2 squared, we can now have the following. I have into biggest bracket of M1, M2, open brackets, U2 squared, a plus U1 squared, a minus 2U1, U2, close bracket, close biggest bracket, divided by M1, a plus M2. We are condensing the expansion. Finally, the change in energy can be realized as I have M1, M2, open brackets, U1 squared, a minus 2U1, U2, a plus U2 squared, close brackets, all divided by M1, a plus M2. With this, change in kinetic energy is going to become M1, M2 all over twice, M1, a plus M2, close brackets, bracket in the numerator of U1
Excuse me, teacher.
minus U2, close brackets. Yes, please.
On the second step,
Up.
okay, I don't understand why we are taking it all out of M1 plus M2, because it's like in the second step, we canceled it out totally.
Yeah. I see your concern.
We canceled it out, then we cross multiplied.
What did we cross multiply if we cancel it out?
No, we first canceled it because it's in the second step, it's out of M1 plus M2 squared. Then we first
We lost
canceled it
one.
out.
We
Yes.
lost one. Do you
Then
see that
after we
one?
cross-
When we lost one,
Yes.
this one which remained cross multiplied up to bring about a common denominator. So it cross multiplied to this term. It's like having A minus 1 over B. When you have A minus 1 over B, it's the same as crossing the A to the B to the A, and you realize AB minus 1 or is over B. Does that make sense?
Yes, teacher.
Yeah. So that's why we have M1 plus M2 as our denominator. Then this one comes from the expansions of A minus B squared. We have worked backwards, gives us A squared minus 2AB plus B squared. Okay? So this is the change in energy or the loss in energy which we attain in inelastic collision. If you have an inelastic collision, type of collision, then just know that the system has lost energy as per that relationship. I will require you to go and re-derive this expansion on your own. You write it down as you put down the notes. You make sure that you write it somewhere and have it so that you can comfortably be in position to expand other long numbers that may be set. If any of you has a question bank, anyone with a question bank for physics, I would like you to go visit paper 1 and screenshot all questions on momentum which have proofs and send me those questions. Actually, send them to the group so that I can discuss some 2 or 3 next time. I know they're quite long, but I don't need to write them down all the time when we're writing questions to make it easier for me to go ahead and simplify. Okay. Unless if some other person has a question. If no question, please take a screenshot. Then I bring something else that we have to show, that we have to discuss. I thought we had one guy in the physics class. How come we don't have the guy today? I mean, are we safe?
So is it that you know all this formula? Can't you just take the last part where the final place in conclusion?
What if they do what?
Is it enough that you derive the whole
They
equation?
can ask you to derive. Everything in physics which is asked, which we do, every definition, every derivation, every proof we handle. In physics, it is examinable. It is in math where the formula cannot be set, or rarely, and they ask you to set a formula or to derive a formula. Okay. And let's try out some momentum number here, which requires just calculation, not derivation. So next derivations, I'll do them. There will be numbers. I'll try them next time. So today, a gun releases a bullet of mass 6.7 times 10 power negative 8 with a velocity of 2.7 times 10 power 7 meters per second. If the mass of the gun is 3.9 times 10 to the power 3 kgs, calculate the recoil velocity of the gun. So if you have a gun, I'm assuming this is our gun, maybe your AK-47. Even has a binoculars. You are releasing a bullet. But before the bullet was inside here, when the bullet is inside the gun, both of them are traced. Initial velocity of the bullet is equal to initial velocity of the gun, which is 0. But after, the velocity of the bullet is 2.7 times 10 to the power 7. Then the gun jacks backwards with the velocity of the gun, which is a negative because it is moving in a different direction, which we don't know, which we are calling the recoil velocity of the gun. So momentum, we said, is always conserved in both cases, inelastic and elastic. Momentum before is supposed to be equal to momentum after. So momentum before is 0 because the velocity of the gun and the bullet were at 0. Momentum after, we have mass of the bullet, final velocity of the bullet, plus momentum of the gun, which is mass of the gun, velocity of the gun. But the velocity of the gun is negative. So we shall have 0 is equal to mb vb minus mg vg. This will confirm mass of the bullet. Velocity of the bullet is equal to mass of the gun times the velocity of the gun. Therefore, the recoil velocity of the gun can be attained from mass of the bullet times the velocity of the bullet divided by the mass of the gun. This will give us the mass of the bullet is 6.7 times 10 power negative 8 times the velocity of the bullet, which is 2.7 times 10 to the power 8 power 7 positive, all divided by mass of the gun, which is 3.9 times 10 to the power 3. Can you compute and give us the velocity of the gun, which we call the recoil velocity of the gun?
.638 exponential
4.6 exponential negative 4 meters per second. Okay.
4.6 exponential.
So we can have that down. So we have the second number. Says a bullet of mass 10 grams is fired into a block of wood of mass 4.99 kgs resting on a smooth horizontal table. If the bullet gets embedded into the block and they move with a common velocity of 8 meters per second, find the initial speed of the bullet. Now we can assume the bullet has a mass small m. Then we can assume the block has a mass capital M. We can assume the bullet has an initial velocity U1, then the block has an initial velocity U2, whereby the block was at rest, the bullet was moving with a velocity of, we don't know. Then they got stuck together, so they both move with a common velocity V of 8 meters per second. So these models can be illustrated on a diagram for just understanding. It's not a must that you have to sketch the diagram all the time, but just interpretation of the question rightly. So if I have this as the, okay, let me assume this is my bullet. If this is my bullet, comes and meets a block. No. This is my bullet, comes and meets a block. Then they get stuck together. The bullet has got embedded inside the block. So this one block has mass capital M. The bullet has an initial mass, velocity initially, which is what we don't know, U1. It has a mass small m. So the momentum before is small m, U1 plus capital M, U2 is equal to, when they collide and get stuck, small m plus capital M times the common velocity. So U1 is what we are looking for. Mass of the bullet is 10 grams. So 10 out of 1,000 times U1 plus 4.999 times 0 is equal to 4.99 plus 0.01 times the common velocity. Therefore, the common velocity is 8 times 8. Therefore, 0.01 U1 is going to be equal to 5 times 8. So U1 will be realized from 40 divided by 0.01. So the speed of the bullet is going to be 40 times 100. And the answer is 4,000 meters per second as the initial velocity with which the bullet would have been fired. Okay. So that's the initial velocity with which the bullet was fired. Unless if someone has a question. Otherwise, if no question, you can stop there for today. Our 1 hour is done. So like I've said, please let's look for numbers in physics papers and physics question bank about momentum. Those of us who can visit understanding, don't forget to visit understanding and do numbers 1 to 10. I told you, for you, since this is not the math class lesson, we shall have to try out a few in physics, but in math we solve all the numbers. So with that, we can have a nice day, since we have no questions.